Welcome back to Agentic AI World. This is episode 9, and today we're tackling a fascinating system design topic, conversational AI platform design. If you're preparing for interviews at companies building voice assistants, chatbots, or customer service automation, this episode is going to give you a serious edge. Let's break it all down. So what exactly is a conversational AI platform? At its core, it's a system that enables natural language interactions between humans and machines. Think Alexa, Google Assistant, Siri, or enterprise chatbots handling millions of customer queries. These platforms combine multiple AI subsystems into a coherent pipeline that can understand what you say, figure out what you want, and respond intelligently. Let's start with the high-level architecture. A conversational AI platform typically has 4 major layers. First, the input processing layer, which handles speech recognition or text input. Second, the natural language understanding layer, or NLU, which extracts meaning. Third, the dialogue management layer, which decides what to do next. And fourth, the response generation layer, which produces the output, whether that's text or synthesized speech. Now, let's dive into each of these, starting with the speech pipeline. If your platform supports voice, you need an automatic speech recognition system, or ASR. ASR converts audio waveforms into text. Modern ASR systems use end-to-end deep learning models. Whisper by OpenAI is a great example. It's a transformer-based model trained on 680,000 hours of multilingual audio. Other options include Google's speech-to-text, Amazon Transcribe, and Azure Speech Services. Key considerations for ASR in interviews include latency, accuracy measured by word error rate, streaming versus batch processing, noise robustness, and speaker diarization. For real-time applications, you want streaming ASR that processes audio chunks as they arrive rather than waiting for the full utterance. This is critical for responsive user experiences. On the output side, you have text-to-speech, or TTS. Modern TTS has moved beyond concatenative synthesis to neural models. Systems like 11 Labs, Amazon Poly, Google WaveNet, and Azure Neural TTS produce remarkably natural speech. Key trade-offs here are quality versus latency versus cost. Neural TTS sounds amazing, but requires more compute. For high-volume production, you might use a tiered approach with cached responses for common utterances and real-time synthesis for dynamic content. Now, the NLU pipeline. This is where the magic happens. NLU takes raw text and extracts structured meaning. There are 2 core tasks: intent recognition and entity extraction. Intent recognition classifies what the user wants to do. For example, book me a flight to Tokyo has the intent book_flight. Entity extraction identifies the key parameters. In that same sentence, Tokyo is a destination entity. Traditional NLU pipelines used a combination of techniques. You'd have tokenization, then feature extraction using things like bag of words or TF-IDF, followed by a classifier like an SVM or random forest for intents, and sequence labeling models like CRFs or ByLSTM-CRF for entity extraction. Raz's NLU pipeline is a great example of this classical approach. It uses a configurable pipeline where you can mix and match components. Modern approaches leverage large language models. You can use BERT-based models fine-tuned for intent classification and named entity recognition. Or you can go fully generative, using models like GPT to handle both understanding and generation in a single pass. This is the approach behind ChatGPT-style assistants. The trade-off is that classical pipelines are more predictable and easier to debug, while LLM-based approaches are more flexible but harder to control. Here's an interview tip. When discussing NLU, always mention the concept of confidence scores. Every intent classification should come with a confidence score, and you need a fallback strategy for low confidence predictions. This shows you think about production robustness, not just happy path accuracy. Let's talk about dialogue management. This is the brain of your conversational system. It tracks the conversation state and decides the next action. There are several approaches, and knowing the trade-offs is crucial for interviews. First, rule-based or finite state machines. You define explicit conversation flows as state graphs. State A leads to state B if condition X is met. This is deterministic, easy to debug, and works great for simple, well-defined tasks like ordering pizza or checking account balances. The downside is it doesn't scale. Complex conversations create an explosion of states and transitions. Second, frame-based dialogue management. Think of a form that needs to be filled. The system tracks which slots are filled and which are empty, and asks questions to fill the missing ones. This is more flexible than pure state machines. Most enterprise chatbot platforms like Dialog, Amazon Lex, and Microsoft Bot Framework use this approach. Third, ML-based dialogue management. Systems like Raz's TED policy use transformer-based models trained on conversation examples to predict the next action. This handles more complex, nonlinear conversations but requires training data and is harder to debug. Fourth, fully LLM-driven dialogue. Modern systems increasingly use large language models with carefully crafted system prompts and tool calling capabilities to manage dialogue. This is the most flexible approach, but requires careful guardrails to prevent hallucinations and off-topic responses. In interviews, a great answer discusses using a hybrid approach. Use deterministic flows for critical paths like payments or authentication, frame-based management for structured data collection, and ML or LLM-based approaches for open-ended conversations. Context handling is another critical topic. Multi-turn conversations require maintaining context across turns. There are several challenges here. Co-reference resolution is one, where the user says, "book it," and you need to know what it refers to from previous turns. Context carryover is another, where entities mentioned earlier should persist. For example, if someone says flights to Tokyo and then what about hotels, the system should understand they mean hotels in Tokyo. The technical implementation typically involves a context object or session state that accumulates information across turns. In LLM-based systems, this is handled by the conversation history in the prompt. In traditional systems, you maintain an explicit context frame with slots that persist and get updated. You should also discuss context window management. In production, conversations can get long. You need strategies for summarization, sliding windows, or hierarchical context to avoid exceeding token limits or losing important early context.